is you have just about the fewest people in the audience because everyone sleeps in. On the flip side, I find the number of you here very encouraging because I assume you're all actually interested in my talk or you'd have slept in too. What I've been working on for the last couple of years is working on making a peer-to-peer live video streaming protocol. So this is like television. You have something that's happening right now, there's a video feed of it, and 1 million people want to watch it all at once. This is a complicated thing to kind of focus in on, so I'm going to take a few different, I'm going to approach talking about it from a few different directions, and hopefully that'll all kind of come together into something coherent in the end. So to begin with, I have to talk about what the goal is. So the basic goal is you want obviously high robustness, high offload, because it's peer-to-peer. So you want very little of the bandwidth to be coming from the original source. You want low overhead, and above all, you want low latency. And that's the thing that's really causes all the difficulties. I'm shooting for latencies of around 5 seconds. Other live peer-to-peer systems make various claims as to what their latencies are. The shortest latency I've had any reasonable claim backing it up was around 90 seconds. So I'm doing a lot better than that, and I'll get into a lot of technical detail about how I make that happen. An important thing to know, an important subtlety about the amount of overhead is there's overhead and there's headroom. So overhead is the amount of extra data you use down the wire in terms of extra bandwidth used. And then there's headroom, which is the amount of extra bandwidth you actually need. So just because there's a certain amount of bandwidth that you in aggregate use doesn't mean that you don't occasionally spike to small amounts of extra bandwidth beyond that intermittently and actually need that extra headroom. So I tend to talk about headroom rather than overhead. And of course, it's very important that there be appropriate congestion control so that you don't need to have every single peer have the exact same upload rate. So you can have some peers with very fast upload rates and some peers with rather slow upload rates, and the thing as a whole will continue to work. I should also note what I am not doing, which is I am not being particularly resistant to attackers. In order to get the latency down, it's necessary to make some trade-offs for security. There are some amount of defenses that one can make to semantic denial of service attacks in my protocol. However, it's nowhere near as much as in BitTorrent, which is very resistant to semantic denial of service attacks, where this one is fairly susceptible to them. Oh, by the way, my laptop blew up right before I flew out here, and I hate PowerPoint, so you're just going to have to listen to me talk. Sorry about that. No slides. So those are the whole high-level goals of what it is that I'm trying to accomplish. So then we need a model of the internet and how the internet works. So ironically, I didn't really know how the internet works before I started working on this. I created BitTorrent without having any real understanding of how it is that congestion control works. My understanding was that you have TCP, which has these pipes, and it does this magic thing where you push data in one end and data comes out the other. And you probably don't want to transfer over too many connections at once because that's bad. It was about my level of understanding of congestion control. In order to make this protocol work, I really had to go down, thank you, go down to the base metal and redo congestion control. This protocol is kind of sitting at layer 4.5. It's technically speaking layer 5 because it's on top of UDP, but it's doing its own congestion control and its own everything. So it's kind of a layer 4.5 protocol, and it kind of blends into layer 5 sort of. Thinking about what the problem is. So our model of the internet is that the Earth is flat. The Earth is a flat disk. And when you, on top of this flat disk, there's this series of tubes called the internet. And the amount of time it takes to get a packet from one point to another is some multiplier on the distance between these 2 points as the neutrino flies. If you look on a world map, you'll note that where we are right now in Spain is the center of the Earth. So then there's this very important concept of how long it takes a packet to get somewhere. Packets mostly arrive in order. Turns out not as in order as it used to be, but the packets mostly arrive in order over the internet. And there are certain things that cause latency and some things that can cause packet loss along the way. The causes of latency between 2 points are, first there's pacing delay, which is on the sending side, you just don't send immediately for whatever reason, generally speaking because of congestion control. You could send some data instantly, but you don't, you wait. So that's your pacing delay. Then there's serialization delay, just the amount of time it takes your modem to turn the data into whatever format it is down the wire. That's generally very small. Then there's the big killer, which is queuing delay. So it goes onto a router. Routers across the entire internet are pretty consistent in terms of how they behave. They have a queue, they plop data onto the end of the queue unless that data would blow their queue size, in which case they throw it in the bit bucket, and then they just send first in, first out as it sends stuff down the wire. That can be huge. That can get into multiple seconds, which is really bad. Then there's propagation delay, which is basically your packet gets turned into a pulse of light. It gets sent down fiber optic cables. The speed of light is about an order of magnitude slower than you'd really like it to be for intercontinental telephony. And so pacing delays can be on the order of hundreds of milliseconds if they're really bad. They should never really be more than like 200 milliseconds if the internet is behaving properly. But they can get to around that high just because of speed of light issues. So take speed of light plus a few more problems with things not quite going straight and just routers acting funky. And something going to the opposite end of the Earth will tend to be that much. We got a little bit lucky about the setup of the Earth because this Pacific Ocean, it turns out, is really big, and you're usually kind of on the same hemisphere as wherever it is that you're talking to. Following that is another bunch of queuing delay on the receiving end. I don't talk about queuing delay anywhere on the backbone because I just assume that the backbone has infinite capacity. You then have queuing delay on the receiving end. That doesn't usually happen because it's unusual for peers to be maxing out their download capacity. And in particular, when you're talking about a live protocol, the bit rate is pretty much fixed. I actually don't have any adaptive bit rate at all. So if a peer actually can't download at the bit rate of the stream, then they're just going to have to eventually give up and leave. So I don't tend to emphasize the queuing delay on the download side very much. Then there follows serialization delay on the download side, which is also very small. And finally, just CPU delays on the receiving end. It can take a while for it to wake up and receive it, especially on Windows. That can be, 10 milliseconds or something, more than it should be. So that's, I'm sure most of you are quite familiar with that model already. As a methodology for how I approach working on this, the very first thing I did was write an emulator of the internet, which behaves exactly as I just said. I've in the past kind of bashed emulation because the emulators tend to not quite work the way the real world works. And of course, I'm violating my own advice here. The reason I got confidence in doing things this way is emulating TCP stacks seems very sketchy to me because real-world TCP stacks are very quirky, and the emulators TCP stacks follow the spec, which is very unlike real TCP stacks. But if you actually get down to emulating layer 4, things are behaving much, much better. That you have these routers, they just follow tail drop. They do pretty much exactly that everywhere all the time. And the only thing you really got to worry about is how big the queues are, but generally speaking, you just assume that the queues are way too big. So set it to some ridiculous value, and that's a reasonable model of the internet. So I have this testing methodology where I can run an emulator where I set up a whole bunch of real peers. I'll typically run tests with like 50 real peers because I can run that a little bit faster than real time on one core in my machine. And those peers don't actually know that they're in an emulator. They think they're talking to the real internet as far as they're concerned, because I've stubbed out calls to sending data on the internet and calling time. And they just use the calls that are passed into them for those things. And so if it's running on the real internet, it's handed the real calls. If it's in the emulator, it's handed this scaffolding that just looks like it. And I really, there's no way I could possibly have gotten my stuff to work if I weren't following this methodology where I can start a whole swarm and run it over and over again and add diagnostic statements and have it run exactly the same the next time. I also go to great pains to make everything completely deterministic. Basically every place where I need to iterate over something in a random order, because frequently these are held in a set or something, I don't want to get a completely non-deterministic ordering out of them. So I will typically sort the elements that I wish to go over randomly and then shuffle them and then iterate over them. This is slightly bizarre behavior. The theory here is that I want it to behave the exact same way every time, with its only dependence being on the seed of the pseudo-random number generator, and this effectively does that. That's my methodology. It does a good job of finding bugs, which turn into just performance problems frequently. With this sort of thing, you get all kinds of crazy emergent bad behavior when you have subtle bugs, and it's good to have something where you can just torture test the whole thing over and over again. So that's my methodology. So in terms of high-level approaches, traditionally when people have tried doing live, they've used a tree approach where you basically decide a priori where all the packets are going to go. This has low overhead. In principle, it seems like it should have good latency. In practice, the latency is kind of lousy. Because of its other big problem is it has really lousy robustness. So you get things at the top of the tree break down, something gets delayed, or a connection just completely drops, and all the problems with that propagate, and then you start trying to fix it, and you wind up having these state machines of how every peer thinks everything is working, which turn into rocket science very quickly as you're trying to fix these things. And you're trying to do it quickly, and then people try and fix it by making it so they're like error correcting packets and try and make multiple trees overlaid on top of each other, and it's really just kind of adding more complexity to try to fix problems. And when you're in a hole, if you find yourself in a hole, stop digging. And so for a long time that was the only approach that I knew, and it just seemed totally unworkable to me, so I didn't even try doing it. Another approach is to make a BitTorrent style protocol, where you have pipes between machines, peers announce what they have, the receiving ends use rarest first to decide what to download, and you basically do it like BitTorrent. This is very low overhead, very good robustness, truly awful latency. It's getting a number of inherent issues that, first of all, it's sending data down pipes, which is a big no-no when you're trying to aim for low latency. A pipe is this thing that TCP does where you shove data in one end, data comes out the other end, and it sends at whatever rate it can, whatever that is in the middle. And the problem with this is that from a latency standpoint, all your metadata gets backed up on this pipe as well, which is inherently adding a whole lot of latency to every single hop. On top of that, it has to incur a triple one-way whenever it sends something. Peer A gets something, it announces to peer B that it has it, peer B then requests it, and peer A then sends it. So this is 3 one-ways just to get something from point A to point B, which is also another major no-no, that you just potentially, even if you get around all these very high latencies involved in pipes, which is what's really going to kill you. That's what's going to get in your latencies into the dozens or hundreds of seconds. Even if you were to somehow get that under control, the triple one-ways make it so you're kind of stuck at more than 10 seconds of end-to-end latency across a swarm as a whole. So that's bad as well. And then it turns out you're kind of stuck with rarest first as your piece selection algorithm, because if you do something that is more appropriate for low latency, you get really, really horrible congestive failures. I actually early on implemented something like that, and actually was only using something BitTorrent like for just like the last 2 hops, and found this really interesting but very frustrating phenomenon that if you're using a BitTorrent style protocol and the peers go, well, instead of asking for the rarest thing, I'm just going to ask for the thing that I need most urgently coming up soonest from this peer that I'm downloading from. What winds up happening there is you have the original source of your data. I call it a source instead of a seed, by the way, because it's not exactly the same thing as a seed in BitTorrent protocol, and calling them the same thing was just way too confusing. So you have the source of the data, and you have some peers that are directly connected to it. And what they're going to do is see this data that the source just made available and go, well, that's not very important because I don't need it for a good long time. That is the least important piece of data for me as far as I'm concerned for my own personal playback. And then they'll wait until the last possible second to get that data. They'll get the data, and they'll play that data just fine. The problem here is the data wasn't just for them. The data was for everybody else as well. And the swarm as a whole never got it. It never really got off the first couple of hops before deadlines hit. So that's an interesting emergent phenomenon, which basically makes it so you're stuck with rarest first, which is also really lousy for latency. So a BitTorrent style protocol has a number of inherent problems with it as far as latency goes. It does have the advantage that it does in fact work, which is something which is frequently a big improvement over tree-style protocols, where getting them to work at all is pretty sketchy. So I think most of the real-world implementations of Live that have been done more or less amount to BitTorrent-style protocols, and they have these latencies in minutes. So there's a third approach which makes people cringe, and which it sounds like I'm joking when I say this, but the third approach is the Screamer protocol, where every peer connects to 3 other peers. And whenever you get a piece of data from one peer that you've never seen before, you send it to the other 2 peers that you're connected to. This has the obvious problem that it has no congestion control of any kind. It also has very high overhead. It has overhead of 100%, which actually isn't all that out of control. That's high, but not totally out of control. Of course, I did make it that each peer has 3 connections instead of more, but three bilateral connections should be plenty because a factor of 2 fan-out is still exponential, still works. The advantages of a Screamer protocol are that it has fabulous robustness and very low latency. It always takes the minimum path it can, assuming the static overlay that you have. But over the static overlay that you have, it always takes the minimum distance path it can to every single node in the entire system. So it has these really great properties, but has no congestion control at all, which is kind of a problem. So my idea was, so I was thinking about this in 2008 and didn't really start working on it until 2009. But the idea that I got in 2008, and this is embarrassingly stupid secret sauce for me to have. My idea was, well, how about I make a protocol where I scream out the data to some fraction of the peers, to like 10% of the peers, or something on the order of 10% of the peers, and do something much more controlled for the remaining bit. Then that way I get all the benefits of the low latency and high robustness to the first 10%. And I'm going to be lacking in congestion control there, but that's okay. I just assume that every peer has some fraction of the download rate in their upload capacity. And it has extra overhead, but again, it's only to 10% of the peers. So an extra 100% overhead on 10%, not a big deal. Like when people do tree-based approaches, they tend to have these like error-correcting pieces, and that tends to be more than 10% of the data anyway. And then I'm going to have more latency and stuff to get it out to the remaining people, but that's not a big deal. That's just a hop or two. And it turns out the best thing to do is to make it so that that's literally just one hop. That you have this very, very strong distinction between things that are potentially not the last hop and one thing that is the last hop, and you treat those as two completely different things, where you allow considerable amounts of pacing delay on that last hop, potentially, even close to a second, and that's not a big deal because it's only adding like 1 second to overall latency, where in every other hop in the middle, you want that down to like 100 milliseconds or less to get from point A to point B, because that adds up. It's multiplying by potentially like 20 hops. If you have 1 million peers and you got a fan out of 2, that's 20 hops. So if it's 100 milliseconds along each of those hops, that's 2 seconds right there. Which is fine, but you can easily start blowing your budget badly if you start adding just even tiny amounts of pacing delays to that. Then every hop can become 200 milliseconds, and then if you have triple one-ways for each of these things, that's 600 milliseconds, and then 20 hops, and you got 12 seconds right there of latency just to blast everything out. Which, it's surprising how quickly that adds up. What I'm doing isn't that far from that. I don't have triple one-ways. I have just one way, and I try to send everything out quickly. But it winds up being 2 or more seconds of just base, can't get away from it, latency of the whole blast out period. But that's not bad. That's smaller than other things. So, so I was still talking about my, so that's the high-level view of what I'm doing, and I started getting into some further detail there that might be a little hard to follow without getting into these. So another view of the whole thing is the wire protocol. Like, what do the actual wire messages look like? So this protocol, even more so than BitTorrent protocol, just reading a spec of what the wire messages look like isn't really all that insightful. It tells you something, but it doesn't actually really tell you how to begin implementing it. It's just missing so much semantic information. But for the purposes of context, I will now describe the wire protocol. There's a BitTorrent style tracker, meaning that you just send it saying, hey, I'm here, and you've now registered yourself with the tracker, and it sends you a list of peers, just a fairly arbitrary list of peers. You take it from there. Peers basically find each other via gossip. You ping peers, get stuff. There's this concept of a connection between two peers. And basically all messages in the entire protocol, other than the ones to the tracker and back, have to do with either forming connections or maintaining connections. And what a connection does is there's peer A is sending peer B. It's a unidirectional connection. It's not bidirectional. And it sends 1/12 of the data. So there's the original source. It's packaging up data to send out to everybody. Each packet of data has a sequence number. It's signed and has a sequence number on it. And there's this concept of clubs. So the club that a piece of data responds to is the sequence number modulo 12. I'll keep saying 12 because I like magic numbers. And I've actually hard-coded it 12 because for a swarm as a whole, it's basically impossible to change the number of clubs midstream. And there's trade-offs to what the number of clubs should be, but because it's a knob that you can't twiddle in any reasonable way, I've simply hard-coded it at a number that's always reasonable. And so I just always assume that it's 12 for the purposes of discussion. So each connection is for a particular club. So peer A will send every 12th packet to peer B. And the peer A doesn't ask peer B if it needs it or anything like that. It just sends it. At the beginning of the connection, peer B tells peer A, here's everything that I have. And under some circumstances, unusual ones, but under some circumstances, peer B will tell A, hey, I also got this thing from somebody else out there. But that's not common. Generally speaking, what's going on here is that peer B is only getting this data from peer A, so peer A can quite happily just send every piece of data as it gets it to peer B. That's important to get rid of these triple one-ways that, like I said, are such horrible killers of latency. Yeah, and then if you drop a connection, you just kind of ping everybody you know and say, hey, tell me about peers that are members of this club. So there's this concept of club membership. Each peer is a member of 2 clubs. And what that means is they get blasted that data. They're among the set of peers that the data gets screamed out to for that particular club. And I hope I'm not getting kind of episodic with my explanation here. So each peer is a member of 2 clubs. So the data gets screamed out to all the peers that are members of that club and then sent out in a much more controlled way on the last hop to everybody. So each peer has a few peers within the 2 clubs that it's members of, and then has 10 download connections from peers who are members of the 10 other clubs that it itself is not a member of. The policy within your own clubs is each peer has 2 or 3 incoming and 2 or 3 outgoing connections. The reason behind this is you want the number of connections you're screaming over to be as small as possible, but you must be uploading on at least 2. Otherwise, you don't have exponential fan out, and you need at least 2 in. Otherwise, you might risk just not getting something ever. And the reason why it can go up to 3, even though you want to keep it to a minimum, is at first I actually implemented it where it was exactly 2, and I maintained this invariance that every peer had exactly 2 incoming and exactly 2 outgoing per club. And the problem with that was maintaining the state machines to make that happen was rocket science. It involved interdependencies between multiple peers to maintain the invariant. And then peers could die in the middle, and it got into these wacky states. And it was horrible. I needed to start drawing state machines just to read my own code, and it never really quite worked right anyway. So I made it so that each peer could have 3 connections, which adds some slop to the code. And what it does now is when it gets fewer than 2 incoming or outgoing connections within its own club, it goes and pings peers saying, hey, who do you know in this club? They give you a list, and you use the person who introduced you to them to do NAT traversal to them, and you ping them, and they send you a pong back, and then you pick one. After you've done that, after a second, you're done with all your pinging. You pick a peer to start downloading from or uploading to, depending on which direction you got below your budget. That peer, then, if it then has 3 or fewer connections, it goes, well, okay, I'm fine. But it's possible that it will have more than 3 connections. So what it does if it winds up more than 3 connections is it takes one of the old connections that it had before, picked at randomly, and it closes it. Without any particular rhyme or reason, it just shuts it down. This can potentially cascade over a few hops of then the peer that was, say, uploading to that one, it gets below its budget, needs to find a new upload. And there can be a few hops here, but sooner or later, you'll hit some peer which only had 2 connections already when the new one's formed, and it'll be perfectly happy with that, and the cascading will stop. This sounds kind of silly and ridiculous, but it gets rid of a whole lot of rocket science, and it's really easy to implement, and it works just fine. The other notable thing about the wire protocol, like I said, was that all the data is signed. This leads to an interesting problem. Peers need to be able to verify signatures as soon as they get them in order to be able to send them out instantly because we care about latency. Which means that you need to be able to fit signatures, have a signature of every single packet which fits within an MTU without taking up too much overhead there. And it needs to use a small enough amount of CPU that an underpowered device doesn't just completely blow its CPU, verifying every single one of these signatures coming in on every single packet. It turns out this is possible to do. I use ED25519, which is Dan Bernstein's elliptic curve cryptography library, and hash trees. The hash trees increase the size of signatures, but they dramatically reduce the amount of CPU usage. They also increase the latency a bit because you have to batch together data every once in a while. I do that every quarter second. And that gets the signing problem under control. Thank you, Dan Bernstein. Okay, so hopefully what I just went through was reasonably understandable. It probably would have been better if I had some pictures. But that's kind of the high-level view of what everything is like. So we're screaming to all but the last hop, screaming within clubs. You have these unidirectional connections between peers. And then we get into the fun part, which is the control loops. Working on this protocol, I've really felt like I'm doing real engineering. Like BitTorrent, I felt like I was doing this computer science exercise of studying something, and the asymptotics are what really mattered. With Live, not so much. With Live, I'm actually dealing with control loops myself, and real constant factors matter a whole lot everywhere. And the end result is an engineering thing with lots of quantitative values going into it. And a whole lot of control loops, and partially because I'm doing my own congestion control, I had to do a lot more real engineering than I was used to. So the control loops are, peers have to decide when to drop a connection. The receiving side will say, I want to drop this connection at points. Oh, I forgot to mention the high-level approach to that. I am doing delay-based congestion control. If you do drop-based congestion control, you will fill up your queues and your latency will go through the roof because you make it so that you have potentially seconds of queuing delay on every single hop. That's a no-go. It can't work. So it's very, very important to make all congestion control be delay-based. So you have to decide when to drop connections, which is done based on one-way delays. When you do drop a connection, it's the receiving side drops the connection generally. You have to decide which new peer to start downloading from. Like I said, you have this simple approach of you just ping everybody that you're currently talking to. You just ask everyone you're currently talking to for relevant peers, use the ones who gave you information about someone to do NAT traversal to them, and then you ping them and then get responses, and then you decide which one to download. So there's a question of which one to actually start downloading from. And when you're uploading, you need to decide what rate to send data at. That one I've spent a lot of time on. And you need to decide, of all the pieces that you have to send, what order of priority do you send them in? Which ones do you send first? Then you need to decide, when you're playing back data to the end user, what rate do you send data to the end user at? And finally, you need to decide when and how much you skip ahead. When you decide some data is just never going to arrive, so I need to do skips and playback. That actually has much more effect on emergent congestive properties of the system than you would think, because when you skip ahead, you tell the peers that you're downloading from that you don't need that data anymore. That's actually very important behavior, because you can get situations where a swarm as a whole is behind. Being behind is bad. Peers start trying to catch up when they're behind, and when you're trying to catch up, you're using more bandwidth than you do normally, and that can make a bad situation worse, and the only way to get out of it is for enough peers to skip enough data that you can kind of get ahead. So there's skip logic as well. So that's 6 control loops. Yay. I do like, when thinking about these, to think from a PID controller perspective. It's kind of weird how the term PID controller isn't really used when people talk about networking, because it's a very, very central concept in control theory. PID is a position integral derivative. Basically, you have some value that's being controlled and some other value that's giving you information about the thing that you're trying to control. So you want to use the information about this thing that's moving around, your independent variable, to make you decide what you do to try and control the dependent variable. So you can look at the rate at which the independent variable is changing. That's D for derivative controller. You can look at just where it is. That's a position controller. And then you can look at the rolling average of what it's been over time, and that's an I integral controller. Most people's intuitions are that they should use D controllers for everything because they're the best. You can't get away with this in networking because you've got packet data, and that's just so noisy. You can't in any meaningful way talk about what derivatives are. And even in most normal engineering, people mostly use P controllers. Most engineering people mostly use P controllers. With a little bit of D. When you're doing these things where you really don't know what you're doing and you're just trying to get it to work at all, it's generally best to just drop off the D completely, because it's even under optimal circumstances, it's only a small fraction of the optimal solution. And actually, what I've wound up doing is moving largely towards I controllers for the stuff that I'm doing here. I was using P controllers, and I'm using I controllers now. A lot of that is that when you're aiming for low latency, you don't want any queues, and so you have no P to speak of. TCP's standard congestion control can be thought of as a P controller, an extremely crude, awful P controller. It detects when it hits the ceiling and smacks itself down by half. Kind of crude. It does work. It is a P controller. So I will now go over these and then take questions, I guess. I don't know how long I am into talking, but so to decide when to drop. You decide to drop when you get a packet that was delayed more than 200 milliseconds over base delay. That is just about as crude as it sounds. The sending side puts timestamps on every packet that goes through. On the receiving side, you remember the minimum one-way delay you've ever seen for any packet from that peer. If you get a packet which was delayed by 200 milliseconds more than that absolute minimum that you've ever seen, you drop the connection. It is very, very rare to get erroneously delayed packets, particularly not that much. That's a pretty big delay for a packet to have. You can have non-congestive packet losses. Those happen for all kinds of crazy reasons. I don't understand why. They happen more than they used to. You can definitely get them on wireless local connections, but the backbone has them more than they should. And actually, in my emulator, on the send message method, it starts with if rand range of 100 is equal to 0, return. That's my approach to emulating non-congestive packet loss. But you don't really get non-congestive delays. They just kind of don't happen. And you can get spikes of cross-traffic doing stuff, but that really shouldn't get up to 200 milliseconds. If you've got 200 milliseconds of cross-traffic, someone's screaming really loudly. So that's the approach that I'm taking, crude as it sounds. The thing that I find a little unnerving about this is it can make it so that when a peer does start getting excessive delays, it winds up dropping all of its connections at once. But reforming those isn't too bad, and frequently it doesn't actually drop them all just because it starts getting kind of close to 200, and then one peer just decides that one packet was delayed too much. So, so crude as it is, it works. Then you need to decide, so one could argue about the 200 milliseconds number, whether it should be more or less. Making it much more is allowing pretty high latencies. Making it much less, I think, is just way too sensitive. Dropping a connection permanently is kind of a hardcore thing to do. This protocol does it a lot more than any other protocol I've ever seen. This protocol just has unbelievable amounts of churn. In a blue sky scenario where there's no cross traffic, peers will very, very quickly come up with reasonably static connections and just stick with them permanently. But as soon as there's any churn, it's just perfectly happy to churn the entire swarm like a dozen times in a couple of seconds before it decides it's figured out where to go. Oh, that reminds me. I forgot to explain why it is that every peer is in exactly 2 clubs. This is a slightly mysterious thing. You can get unlucky in your club allocations. If every peer is a member of only 1 club, then there can be a club that just happens to have less capacity than the others. And this will dramatically reduce how well, this dramatically increases your necessary headroom because it means you need a lot more extra overhead because you're hobbled by your worst club. And you can try and get cute and fix this by putting in an error-correcting club. That turns out to be not such a hot idea. It inherently increases your latency. It inherently increases your overhead. But most of all, it doesn't work. You can have the situation where you take the half of your clubs that have less capacity and the half of your clubs that have more capacity, and that lower half cumulatively just might not have enough. It might be more than 1 club's worth of data under what it really should be. And it turns out that that's quite likely if there's any variation in the amount of data that clubs have at all. So it works a lot better if every peer is just a member of 2 clubs. Then it turns out load can naturally shift between clubs. And in order for things to get really bad, you'd have to have like 1 club that had like less. You'd have you have to be off by a full factor of 2, and you're getting unlucky in order for it to not work. So, so the other advantage, of course, to every peer being in 2 clubs is that it's really trivial to implement. And I like that. But it also, I believe, is the best solution. So the idea there is you just put every peer in 2 clubs so that load can move between clubs naturally, and that just happens as an emergent thing when you have a properly working set of congestion control algorithms. So I like those kind of elegant solutions. So anyway, getting back to what I was talking about before, you then need to decide which new peer to download from. You just dropped a connection, you pinged a bunch of peers, and they gave you some kind of information, and you did NAT traversal to all of them. So you can pick any of them to download from. And you have to decide which one. And this is something that I realized the right way to do it actually just a couple of weeks ago. When you ping a peer in its response, it tells you how many upload connections it currently has, just a number. And then you pick randomly among everyone who gave you pongs, proportionally weighted by their current number of upload connections. The idea here is that you want load to increase kind of proportionately everywhere. Presumably, everyone got their current number of uploads based on prior congestion control information. And they're all about right. And so ideally, you wouldn't have to give them any extra load, but you do because you need to download this stuff. So you want to kind of evenly spread it out among everyone, and the best way to do that is proportionately weighted by their current just pick at random, proportionally weighted by their current number of upload connections. That works really, really well. I was previously using round trip times, which is a bad proxy for current upload queuing delay, and that's better than random, but not that much better than random, where this algorithm is a lot better than random. The amount of time it took my peers to kind of get out of the nightmare scenario where you just start a whole bunch of peers with very heterogeneous upload capacities and really hardly any headroom at all, and just time how long it takes for them to kind of settle down and stop churning. And that was previously like 45 seconds, and it just dropped to 15 seconds after I made that change. So that's a very important heuristic to have in there. Then you need to decide the rate to send. Oh, so I'd like to point out which new connection to form, because you're using the current number of upload connections each peer has. That is most definitely an I controller, because you're using this aggregate information over time, where the when to drop is a P controller. I think I've had this trend towards I controllers because the data that you have is so inherently noisy that even P controllers are kind of overreactive. So then you need to decide what rate to send at. The way you decide what rate to send at is the source encodes the bit rate in the messages. It just tells you what the bit rate is. And each peer takes the bit rate divided by the number of clubs, which is 12, times the number of connections that it has, and it sends at a little bit faster than that rate. I say a little bit faster because you don't want to send at exactly that rate, because you can get into a situation then where you have a pacing delay. Just for whatever happened, you got extra data. You fell behind by a bit. And if you just send at exactly the right rate, that backlog will never really disappear. So you want to make that backlog disappear. In order to get that backlog to disappear, I take this I controller that I have and I add in a little bit of P. The way I do that is I look at the current pacing delay. Pacing delay being how long it would take to flush out all the data I have to upload at this calculated raw rate. And I take that in seconds times some parameterizable constant, which I believe is set to 1 right now, add it to 1, and multiply the send rate by that value. So if you have no outgoing queue, you send at exactly the right rate. And if you have some outgoing queue, you send at a little bit faster than the ideal rate, going up, increasing as the size of the outgoing queue increases. Oh, and just as a sanity check, I put a cap on the multiplier at like 1.5, I believe. That sounds eminently logical. You might wonder what else I could possibly have thought was a good idea for that. I have tried many things. That's probably the one line of code that I've spent by far the most time on this entire project, and I've done all kinds of crazy things there, and it worked really horribly at various times, and it's bad. Anyway, that even though it sounds totally obvious that that's the right way to do it, it was not obvious to me to begin with. Then there's a question of what priority do you give to your pieces. You have a bunch of pieces that you need to send to a bunch of peers. What order do you send them in? So you've decided, okay, it's time for me to send a piece. I have this rate-based congestion control where I just send a packet every once in a while based on my current calculated rate, which I really like doing. I'm really fond of rate-based congestion control. I find congestion window-based congestion control very unaesthetic. And I'm very happy to be using rate-based congestion control here. But you've now decided, okay, I'm going to send a piece now. Which one do I send? That's a surprisingly subtle problem. Obviously, you prioritize all the in-club traffic over all the out-of-club traffic. So that's just a given. That must be done, with an exception I'll get to in a second. But then, which one do you send? And it turns out doing it strictly based on which packets are most urgent is a really bad idea, because you can get some peer that joins you that has kind of a significant backlog of things that they need, just because for whatever reason they got messed up, they got a backlog. And you don't want to immediately spend all your time filling their backlog. You got other peers to send data to. So it turns out the best thing to do is to round robin peers. You set up an in-club wheel and an out-of-club wheel. And you go through the in-club wheel, like moving the first one on to the end, if you've still got data for them every time you send a piece out. And then if your in-club wheel is empty, you go to your out-of-club wheel and you do the same thing there. This works very well. There's one interesting wrinkle here, that if you have a situation where you have a whole lot of in-club connections and only one out-of-club connection, it's pretty easy for that one out-of-club connection to wind up getting starved. It can't get 100% starved, but it can wind up taking like several seconds to send it its next piece of data, which is really, really bad. This can particularly happen on the source, which has way more in-club outgoing connections than anybody else does. And it was, I noticed this starvation happening in my emulation one day, and it was a really interesting experience figuring out what was going on. I was really scratching my head over that one for a while. The heuristic I figured out that solves this problem quite adequately is you just have a rule that every 10th packet must be out of club, so that the out of clubs can never really get starved. You just remember how many packets in a row you've sent in club, and if the value is 9, you send an out of club packet, reset the value to 0. So then there's the playback rate and skips. So there's this thing that I call the smoother, which is what actually sends out the data. It gets this data in kind of noisy order as the data is received, and it sends it to the playback thing in something like a coherent time rate. I'm using Flash Player. Flash Player has its own smoothing. It corrects way, way too fast. It'll play at like double rate or something like that. So what I'm doing is I'm just pretending that Flash Player always instantly plays all the data that you send it, and I send it data on a very coherent schedule to try and make it behave the way I want it to. So on the source, I'm like marking down timestamps on all the pieces of data as I get them. I then batch them up into these bigger pieces. But when I'm playing back, I try to play back on exactly the same schedule that everything originally arrived on the source. Yeah. So the problem here is, what do you do if you don't have data to play back? And what do you do if you're playing back with too high of a latency? And then when do you decide to skip, which has to do with what do you do if you don't have your next piece of data? So by and large, if you don't have your next piece of data, you wait. I used to have heuristics in there to try and like slow down playback if I thought it was running too close to some limit. It turns out that's not such a good idea. Freezes, like very quick freezes like that, even freezes for a second or so, are pretty intuitive to humans, where slowdowns are not. So what I'm doing is, if I don't have any data to play, well, that sucks. I don't have any data to play. I'm going to wait. Then you can sometimes get into a situation where the weather was bad on the internet at some point in the past, and you wound up with a latency of like, I don't know, 6, 8 seconds, something like that. And you decide, you know what, I'm playing with too high of a latency, what do I do now? Now, you don't have any good answers here. You have several unpleasant possibilities to choose from. You can keep playing at the higher latency until the end of time. I don't really like that option very much. You can just skip a couple seconds worth of data. I really don't like that. That is very unpleasant to the end user, because it was like the critical scene and the thing that the person's watching, and oh, we skipped ahead, sorry. That's really bad to do. And then you can speed up playback, which is what I wound up doing. So it's playing back, I believe it's set up to 10% fast now. I should probably reduce that to 5% fast. That's not that human perceptible. It's doing it in a way where it doesn't change the pitch of the audio. If there's music playing and it starts speeding up or stops speeding up, you can notice the rhythm change, but mostly it's okay. And then when you're paused, you will sometimes notice that you're only missing a little bit of data and that you have extra data afterwards to send. So there's this question when you have extra data, do I send this data or not? Do I play back this data and just skip whatever was missing, or do I keep waiting for more data to come in? And what I wound up doing here, and this is kind of ugly code, and maybe I'll figure out something better to do in the future, is because peers are so good at sending out the data to each peer that's supposed to go to in order, I keep track of which, basically in Smoother, I keep track of which peer I got data from, and I keep track of which peer I got data from. And if there's a changeover in peers I got data from, then every time I backlog potentially data from the old peer, because it might not be in order because data was lost. And oh yeah, so I only send data, I only actually process data when it's the next sequence number up from the current peer that I'm downloading from to make sure I kind of get stuff in order. And if it was actually skipped there, I assume it's really and truly skipped. And then I do some really ugly stuff in peer changeovers. But mostly when I think I'm ready for the data, when the packet lossage potential issues are corrected for, I process the data, and then whenever I get just extra data that can be played and there's something missing, I go ahead and skip. I don't know how understandable that was. The logic's kind of ugly, actually. I don't really like it. I have to say the smoother is the thing that I hate working on in the code base the most. It involves a whole lot of time, and I'm using monotonic time everywhere and have to worry about clocks all not being synchronized and worry about CPU delays happening and what do I do about CPU delays. And time is not interesting. It is simultaneously very subtle and very difficult, and you will never ever come up with any actually interesting novel insight having to do with time. So I hate dealing with that. But I believe that covers actually all of my control loops. So I've kind of covered the basics of everything that I meant to. I hope that was reasonably understandable. And how much time do I have for questions?
Probably we have like 5-10 minutes.
Oh, okay. So I have time for questions. Anyone have any questions? Yeah. Yes. It's delay based. So if your queue is more than 200 milliseconds, then it will be TCP friendly, in that it will yield to TCP, and the local peer will probably eventually basically give up if TCP is running. But it mostly will yield to TCP. It has some minimum that it's trying to send at, so it'll keep bumping up close to the minimum that it really wants to send at. But TCP will generally cause your outgoing queue to be a lot more than 200 milliseconds when it's filling everything up. It is not UTP friendly. It'll drown out UTP. Yeah, or well, even that's not simple. It'll drown out UTP if UTP is set to the standard default of 100 milliseconds. If UTP is set to more than 200 milliseconds, UTP will drown it out, but that's not generally done. However, it makes sense for this to drown out true background traffic because presumably a live stream is something you're actually watching and is not background.
Why do you want to be TCP friendly? I don't want to be TCP friendly when I'm watching real-time video. Be TCP respectful.
TCP is a giant bowl in a china shop. And I unfortunately need the china to be intact. I need my latencies to be low. So I intentionally am queue friendly, that I'm trying to keep the queue empty at all times. And while I will only engage in congestion control when the queue gets up to 200 milliseconds, that should hopefully not happen very often. That most of the time, the queue is essentially empty. I'm sending in a rate-based controller, so I'm sending at a very steady rate, and I'm sending at a rate less than the capacity. So the queue should usually be empty. And I need that because I want my latencies to be low. And of course, there's cascading latencies that add up over the whole thing. So it's very important that at every single hop, the queue be as small as possible. TCP will, by itself, without any encouragement from me, make the outgoing queue be so bad that I find the connection completely unusable. So there's nothing I can really do about that. TCP just kind of sucks.
I have two questions. So, well, first is probably in the next years in the P2P edition there will be here paper analyzing your protocol. So they will go crazy trying to justify your magic numbers and all these things.
Yeah.
So my question is about the topology that you are creating. So you say this magic number 12. So there are 12 clubs, but you belong to 2 clubs.
Yeah, so there's a coherent reason why peers belong to two clubs. You don't want peers belonging to, you want peers belonging to as few clubs as possible, because for every club that you're a member of, this increases the number of connections that are in club which don't have congestion control operating on them. So you want to be in as few clubs as possible, and you want every peer to be in two clubs, because if every peer is only in one club, then you tend to get situations where there's a club that just doesn't have very much upload capacity, and that's really bad. So you put each peer in two clubs, and then the congestion control will naturally tend to make it so that when a peer is in two clubs, it will upload more to the club that needs it more, that it's a member of.
But you said that, but there are 12 clubs.
Yeah, so there are 12 clubs. So you have, the reasoning there is there's this trade-off where if you have a very large swarm, more clubs tends to work better because you have much more fine-grained control over the amount of uploading you're doing, and the minimum amount of upload each peer can do is less. So peers with truly awful upload rates can do a better job of contributing. So you might want there to be like 20 clubs or so. But that doesn't work very well for small swarms. If you only have like 2 peers in a swarm, then with 12 clubs, those 2 peers can only upload 1/6 of the data to each other, just because that's the only stuff that they redistribute to everybody else. So there's this trade-off between having offload in small swarms versus working just vaguely well in big swarms. And really small swarms, you probably want like 8 or 6 for really extremely small ones. And really big ones, you probably want like 20. So I just kind of settled on 12 after some experimentation. A swarm, you cannot dynamically change the number of clubs in a swarm. Like you're sending at, you have this formula, it's the sequence number modulo the number of clubs, and there's just no way to change it midstream, and it would be extremely difficult to try and set up logic to do that. There'd just be a whole lot of state to change in crazy ways. At one point I did make it parameterizable so that you could, so that the tracker could pick for each swarm how many it was, so if someone was going to host something, they can guess a priori, but it's like long in advance that you have to guess how many peers are going to be watching it, and if it's only going to be a handful, you can use a smaller number. If it's going to be a lot, you set a big number. And then I realized I only had one tunable parameter on my tracker, and it was something which most people are going to have no idea what to set it to, and they're always going to do it wrong. So I decided to remove the one knob. I decided having one knob with a giant "don't move this" sign on top of it was a really bad thing. I just removed the knob completely. So the number of clubs is 12.
And my second question is, your emulator and this technology will be open source? Or?
Well, funny thing with like BitTorrent, even though BitTorrent is open source, most clients out there are running our code base anyway. And I'm planning on making it so that I have full auto update capability in all clients of my protocol so that I can fix stuff in the future, because I'm anticipating needing to do that. And this is a very finicky protocol to implement properly. Just because you have a spec in front of you doesn't mean you can implement it in any reasonable way. You need a lot more semantic information than is just included in the wire protocol. So just in the interest of making everything work well, I'm not going to be encouraging alternative implementations, because I want that control to make the ecosystem work well. I am planning, haven't made final decisions how to do this. I'm planning on making my code base available to academics so they can study it and draw conclusions about it, including my emulator. My emulator is extremely simple, but I think it's important that people have access to that because it's a very, very good tool, and I've spent an awful lot of time tweaking this kind of silly command line utility I have for running tests, which gives you really the exact information you really need to see what's going on. And I don't want people to spend a lot of time redoing that work badly. I think it's important, if people want to study my stuff, that they have my development environment and start off on a good foot just to begin with.
About how do you exploit capacity heterogeneity? Because as far as you mentioned, when you choose the number of outgoing clubs, then you're trying to...
So each peer has a mostly fixed number of incoming and outgoing connections in the clubs they're member, in club connections. However, you have an arbitrary number of out-of-club connections. So you're uploading to leaf nodes for the clubs that you're a member of, between 0 and infinity of those. And that's the thing that can vary tremendously. Does that answer your question? Yeah.